Okay, everybody, we're going to talk about the last. However, as bonus material, if you wanted to, you could look up Gauss, Gauss. Okay. If I can make some videos on him and get him uploaded as well, I will, just because I feel like he's a very influential mathematician on modern day mathematics. And he happens to be one of my favorite mathematicians, so if I have time, I will get that up there and you can take a look, or you can just go look at Gauss for yourself. It's Carl, C-A-R-L-F. F stands for Friedrich Gauss. However, the last bit of official material that we just absolutely had to get through for the course is Newton and Leibniz. It's something that's called the calculus controversy. We'll talk about that in a little bit. The calculus controversy is the second controversy for our course. We, of course, had the cubic controversy, where we talked about Cardano and Tartaglia, and now we're going to talk about Newton and Leibniz. I think that if you are a math person, you've probably heard that Newton invented calculus, and that's not wrong. However, it's also not entirely true. Okay, so we're going to talk a little bit about both of these mathematicians. We'll discuss how their paths crossed and what each of them did and did not do to help things. And I believe I've uploaded a PowerPoint on Newton and Leibniz, the controversy, and also one specifically about Leibniz and his notation, because it's really of importance to our study that we consider particular types of notations. So let's start out with Isaac Newton. I'm sure that everybody has probably heard this name before, both in math and science. He is put up as someone who is to be revered, and we're going to find out some of the reasons why. His dates are 1642 to 1727. He is English. So if we're looking on the map, I think I might have one here with me. Maybe I left it, but on one of the more recent videos, I pointed out, I'm sorry, I don't think I brought the map with me, but on one of the more recent videos I pointed out, not only have we moved into Europe talking about the French and the Germans and things like that, but now we have also moved on up into England, which is its own little set of islands, right? The UK. So Isaac Newton was English. His mother was widowed twice. And that's not so important, except that both times she ended up as the heiress to big estates. Okay, and that is important. Newton was a small kid and left alone. His father died before he was born, and then his mother left him alone as she took her second husband, and then by the time that he was 11, she was able, because she was in control of both of these estates, she enrolled him in what was called the King's School. Okay. So the fact that she was this heiress to two big estates actually was the thing that funded his education, which is a useful thing for him. There's a story that he was in a fight whenever he first got there and to the King's School, and that he wanted revenge. Okay, and his way of getting revenge was to concentrate on his studies. I know, big Brave guy there, right? Tough guy. Okay, he wanted to concentrate on his studies, and he wanted to best the guy that he was in a fight with, and in fact, he became first in his class. Okay, so he poured a lot of efforts into being a smart kid, which is not a bad thing. All right, so he is actually one of the forerunners for some of the weird experiments, I'll put that in quotes, weird experiments, that you might have heard about for other people. For instance, he is said to have flown kites with lanterns on them attached to them at night. He's trying to do some studying of something. I don't know what that's for, but that's one of the weird experiments that he is known for. He was said to do a lot of designing experiments to test hypotheses that he had. If he thought that something was true or not true, if another mathematician or scientist had put forward some kind of a theory, then he wanted to test it, and he was really big on designing experiments that he could test those things. Okay. As he got older, he studied at Cambridge University. It's a school we probably have heard of before, right? It's very well known. However, he was alone while he was there. He didn't have a ton of friends. He was known for being a loner. And so one of the things that he did while he was there is he studied Copernicus, who was before his time, but Copernicus and Galileo and Descartes. So some famous names that not only in our course, but probably some of them other people had heard before our course. And he sees that and he studies those on his own. He's able to get a hold of materials and really do some in-depth studies. Okay, so here's what happens. In 1665, the plague comes to London. Well, it was already there, but the result is that it shuts down Cambridge. So the idea being that people realize there are too many people in too small of an area, all on top of each other here in London. So if we disperse, then we can help not spread the years ago. However, it's interesting that it mirrors a little bit what 4 years maximum here. And he was, like I said, very productive while he was at home. So here's some stuff that he came up with while he was in the country. One is a paper he called The Theory of Colors, Colours, in the English tradition. Theory of colors, and that particular thing is the study of white light. And basically, everybody has probably just takes this kind of for granted. It's an optic study where you look at, for instance, you can hold up a crystal and let light pass through it. When the sunlight enters the crystal, it's white. When it goes through the crystal, it's refracted inside of there, reflected inside of there, whichever the scientific term is, sorry. But it comes out on the other side and it looks like a rainbow. So we all have seen that. We've seen light coming through water droplets and it creates a rainbow in the sky or a rainbow on the ground, different things like that we've seen. And the idea here is that white light is actually the combination of all the colors, basically. So, for lack of better words, please forgive me, my scientific friends, can be broken down into the colors of the rainbow. That's his thought process. And actually it said that all the colors can be found in white light. So that's the theory of colors that he came up with while he was in seclusion. Okay. The theory of gravity. Yay. Okay, the story goes about the apple and so on and so forth. It's actually been more or less proven or shown that the apple did not hit Newton on the head. However, the story, I think in your book, goes that he was sitting under a tree and he saw an apple fall, and he wondered, what force is it that brings that apple to the ground? And that's what started making him think about this force that we would call gravity. So that's the more, I guess, realistic probably story. Okay, and then he had a study of infinite series and tangents, which all of us have probably studied calculus, and we know that this study of tangents and infinite series leads us to the idea of limits, which is a basic calculus concept. And it's really worth noting that all three of these he had by the age of 24. So by the time he left the country after 1666, he had all three of those pretty well developed, and he was just 24 years old. Not very old at all. If you read some of the quotes in Newton's work, he says that basically this was a time in his life when his mind was still active and that kind of thing. The problem with Newton is that even though he came up with all of these things, he was still very solitary, and he told no one. He's not sharing his information. And as we saw whenever we were doing the cubic controversy, not sharing information in the world of math and science might actually get you into a little bit of trouble, which is where we're headed with Mr. Newton. Okay. So that's kind of the idea that's going on here. But he has developed these things. He has papers on all three of those theories. And what you'll see is that when he goes back to Cambridge after the plague is over and he becomes a professor, he has a mentor who sees his paper, his papers. And the mentor, what he does is, his name is Barrow, B-A-R-R-O-W, by the way. What he does is he takes Newton's paper, in particular the one on calculus, and he takes that paper to something that's called the Royal Society of London. Now, there's a PowerPoint I've put online. I did not make a video on this one, but there is a PowerPoint I put online into your learning management system that talks about the development or the beginnings of social organizations such as the Royal Society of London. And what happens in here is that in this particular one, it's made up of mathematicians and scientists who in particular value theories that are developed, and if you have experiments that either support an existing theory or create a new theory, if you have inventions, different things like that, if you've done those things, then they appreciate your work and you can become a member. Okay, so when he gets back in, I would say 1667 probably, his mentor shows his paper around and his name becomes known to these people in the Royal Society. However, Newton refuses to publish. And there's several things that are going on behind them. One of the stories is that he's tried to publish once before and that somebody took some credit for some of his work or tried to make it seem as if he were plagiarizing, and we all know what a bad thing plagiarism is in academics. And so perhaps it's that, perhaps he just doesn't want to share his knowledge, but there seems to be several different things at play for why he refuses to publish. However, in 1669, he's the first to create a reflecting telescope. Now, we mentioned the telescope before. For instance, Galileo created one that could see 20 times more powerfully than any other telescope that had been made before it. But this reflecting thing, what it does is it allows Newton. Oh, and there's a PBS video. If I can find it, I'll link it into our course. There's a PBS video about Newton, and he's the first to create this reflecting telescope. And what it does is it basically uses a series of mirrors inside of the tube. So there will be a mirror slanted this way and a mirror, I don't know how they go, but mirrors inside of there that kind of reflect back and forth the image, so that even though you're bringing a small image here, like the moon or whatever, it appears very large by the time it gets in here because it's been reflected back and forth. So by the time it reaches your eye, it seems very large. That's the idea. So what the deal is here with this reflecting one is that you no longer need a huge, long tube. That we needed before. Okay, Galileo was able to make one that you could see 20 times stronger, but it required a huge tube, a really long tube. With this one, what it was said is that Newton could use a 6-foot tube to do the work previously that would have required, let's say, that previously required a 60-foot tube. I can't write. Previously required, sorry guys, a 60-foot tube. Okay, so that's kind of the idea behind this. Because of that, it's such an impressive invention that in 1672 he is made a fellow in the Royal Society. He becomes a fellow in the Royal Society. All right, so he gets there even though he won't publish the book or publish his papers on, in particular, the calculus. He had to defend himself previously in different things. So he doesn't want to do that, but with his reflecting telescope, he clearly is the only one who has one. And so they're able to pass it around amongst the fellows, the other people at the Royal Society, and he gets the recognition for that and becomes a fellow. So that's kind of cool. All right, let's talk about this other guy, okay? His name is Gottfried, Gottfried, I believe. Gottfried Leibniz. 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 All right, his dates are 1646 to 1716. Okay, and he's born in a town called Leipzig. Leipzig. So if you'll compare for just a second, let me show you. Newton was born in 1642. Leibniz is born in 1646. This makes them contemporaries. It means that they're growing up at about the same time. Newton lives until 1727, whereas Leibniz dies at 1716. So Newton's born a little earlier and doesn't die for about 11 extra years. So he's older for sure but still they're living at the same time. So that's what's important here. They're growing up in the same times and with the same background materials, with the same Copernicus, the same Galileo, the same Descartes, things like that, to work off of. So that's interesting. The neat thing to know is that on his own, they often say independently, because they want to make sure that nobody accuses Leibniz of plagiarism, basically. He duplicated Newton's findings in calculus. Okay. This guy, as a young kid, he had access to a lot of books because apparently his father had a library. So he did a lot of reading and self-teaching and that kind of thing. He went to University of Leipzig. And he was actually in his teen years whenever he received degrees in law and philosophy. One a bachelor's, one a master's. And then he went to the University of Altdorf because for some reason Leipzig would not give him a doctorate of law. One of the theories out there is that they felt that he was too young. But he did receive a doctorate of law from the University of Leipzig. And the interesting thing was that this happened by 1667. Now, if we look at his dates, 1646 to 1667, he was 21 years old. By the time he got his doctorate, by the time he turned 21, he already had a doctorate of law. Okay. We also see this is 1667. This is the time when Newton has already made his big discoveries, the three that we mentioned before, right? Okay, theory of colors, gravity, infinite series. This happened during 1665 and 1666 while he's at home. So Newton's already making these huge discoveries, and Leibniz is doing math as well, but he's working in different ways, okay, at the university. All right. It said that he kind of became a partner with a guy named Baron Johann Christian, and I'm sure I'll butcher this name, von, and I'll say Weinberg, Boineburg. He worked for or with him kind of as a partnership. The big thing that Leibniz did that was later acknowledged and somewhat with this Baron Johann Christian, his help, is that he created what amounts to a calculating machine. In fact, he published a paper that basically was the beginnings of what we would now call modern day computers. So he shows a lot of circuitry kind of things and the what I guess nowadays we might call a motherboard or something like that. Just the decision making, the algorithm, the process, that kind of stuff. He developed the actual calculating machine, but he also had the basics of a computer, which is really, really interesting. So by 1673, he becomes a fellow of the Royal Society. let me check that. I'm sorry. I want to make sure that that's when he became a fellow. Yes. So what happened is that they gave him membership. Sorry, the Royal Society of London. They gave him membership based on the creation of his calculating machine, much the same way as Newton became a fellow through the creation of his reflecting telescope, right? They both kind of made these great inventions. The society could see that they were worthy of being, they would help advance math and science. They were worthy of being studied, and so they gave them fellowship into the Royal Society. Okay, so interestingly enough, he becomes this fellow, and he makes this calculating machine 1673. If we go back up just a little bit, it was 1672 when Newton became a fellow. So Newton probably could have become a fellow way before then, 1666, 1667, whenever he came back to London, but he wouldn't publish. So he had to wait until he had a creation that was not published, that they were willing to give him credit for, basically, to become a fellow. Okay, so what happens is Leibniz is visiting the Royal Society in London. He has been doing some work with this partner of his in Paris. Let me throw that in there. So after he visits the Royal Society, he goes back to Paris. He's heard rumors about this calculus thing that Newton has, and this is where he actually duplicates the findings. So he's heard rumors, he's heard a little bit about it, he has an idea of what Newton is looking at, what his calculus entails. He did not look at any of Newton's notes, he did not, story goes, plagiarize anything from Newton, but because he has a concept of which direction to go, he goes back to Paris and independently creates calculus. Okay, so the interesting thing for us here is that Newton certainly created, if we will, calculus first, 1666, right? So he obviously had that knowledge first. This is 1673. So many years before Leibniz gets around to doing this, he does. Newton had it. However, Leibniz was smart enough, and he had the mathematical chops to be able to independently create calculus. And there's one other thing about Leibniz that's really important here, and that is notation was extremely important to Leibniz. In fact, one of the PowerPoints that I've posted in your course talks about how important notation was to Leibniz. In fact, he was trying to find some kind of universal notation that he could use to explain people's logic and life and just the universe around him, basically. He was looking for notation for that, and so he was kind of hung up on the notation. It's actually kind of a good thing for us because we see that it pays off for us, and I'll show you how in a minute. Okay, so the problem is that he certainly did not create it first. However, he might have done a better job with some of the creations than Newton did. So 1666, he wrote a book, De Arte Combinatoria. Okay, which basically means the art of combinations, or that kind of thing. And what we see in here, this is where he put out his early model for the computer. Okay. We also see at this time that he's looking for universal characteristics. So things that he can use symbolically across culture, across different things. And because he believed that everything is connected, he studied everything. So he was a philosopher, he was a scientist, he was a mathematician. He just studied everything. And there are quotes out there that say that Leibniz actually forwarded more notation than anybody else, and the notation has stuck for a lot of his things because he was very thoughtful in the way he put forward his notations. So in 1675, he came up with his limiting notation. Okay, you might recognize it. It goes LIM, X goes to infinity, that kind of thing. Okay, he came up with ways that calculus can be useful. Okay, in everyday life. So, uses of calculus, things we can do with them. And he wrote to the Royal Society. Now, this is something that Leibniz did correctly. He knew that Newton had created calculus. He wanted to publish with him. Okay, so he wrote to the Royal Society. He asked them to please converse with Newton and see if he would work with him on a publication. I have the calculus also. I have this lovely limiting notation that Newton does not have. Okay, so this is unique. So he's done some stuff to further, basically, calculus. Please, please, please encourage Newton to publish with me. This is in 1675. And basically what happens is that Newton writes a couple of letters back and forth where he's basically kind of accusing Leibniz of plagiarizing from him. And of course I'm the one that did it first. I'm not going to publish. He still refuses to publish. However, what he does do in one of these letters is he's very secretive, but he writes the key to his calculus, key information for his calculus, in an anagram. Okay, now an anagram is something that basically stands for something else, right? So it might look like gibberish to us, but if you know how to unlock the anagram, it will give key information about the calculus. It's kind of his way of proving that he has the material and he did it first. So, I'm going to say he had knowledge of calculus first, because he's kind of documented it in these anagrams now. So if I give you the key, you can unlock it, and then you can see my calculus, but I'm not giving it to you because it's mine and I don't want to share, that kind of thing. So in 1676, he calls Leibniz basically a distraction. So the Royal Society is trying to get him to communicate, trying to get him to publish. He's like, here, I wrote you 2 letters back and forth. I'm done. This is a distraction. My mind is on other things, and I don't have time for this mess. Basically, he's a plagiarizer, and send him away. I don't want to deal with him. That's what he does. All right. So with that kind of a response, what happens? Well, Leibniz gets tired of waiting. Because remember, let me come back up here. He's had his limiting notation since 1675. He went to visit the Royal Society in 1673. So in 1676, Newton basically tells him, no, I'm not going to publish. So what happens is that Leibniz published, okay, in 1684. Now, remember that Newton has known since 1665, so almost 20 years, Newton has been sitting on calculus and not sharing with the world. Okay, so this is, we know this is wrong of him to keep this knowledge from mathematicians, because mathematicians want to use it and move things forward. So Leibniz finally publishes in 1684, which, by the way, is getting close to 10 years after he knew about calculus, right? Because he visited the Royal Society in 1673. So he's like, well, when was it? Yeah, he visited the Royal Society in 1673. So it's 11 years. I've been developing calculus. I've been developing the notation. I've been trying to get you to publish. You won't publish, so dang it, I'm going to publish. So that's what he does. Newton feels like he's been backed into a corner, and so he finally publishes something called Principia Mathematica, which of course is Principles of Mathematics. And he did this in 1687. Okay, so you can see the controversy, of course. The controversy is Leibniz managed to publish it first, 3 years before you, of who owns it and who's the plagiarist. Arguments ensue. Leibniz is called a thief, basically. It goes back and forth, that kind of stuff. And it really gets nasty, of course. This is in 1680s, the 1680s, and this goes on for decades, guys. I'm just letting you know, forever. So finally, what happens, if you'll remember, Leibniz dies in 1716. So he's feeling, I guess, a little old, feeling toward the end of his life. I don't know. But a couple of decades later, in 1712, Leibniz wants to clear his name. Wants to clear his name. He's like, look, I did not steal from Newton, even though some of Newton's patrons and followers have been accusing him of this. He wants to clear his name. So what does he do? He appeals to the Royal Society. Please investigate. I need to clear my name. I didn't steal this, basically. All right, so that's all well and good, and that's probably the right thing for Leibniz to do. The problem is that basically he waited too late. He waited too long. Because by the time that Leibniz appeals to the Royal Society, some changes have been made in the Royal Society. And the biggest one that's of importance to Leibniz is that Newton is now the president of the Royal Society. You waited too long, man. You should have appealed earlier. This causes a problem, of course, because Newton is the president, and of course, what's he going to do? Leibniz is asking for an investigation, so he does instruct some fellows. I think the secretary and some different ones. Members of the Royal Society, they call them fellows, to investigate. However, I mean, think about it. Do you really think that these people who are fellows in the society that Newton is the president of are going to come back against him whenever he's clearly exhibited. Not only does he have a mathematical and scientific knowledge in mind, but you know, he's the president, so he must have some kind of also diplomatic ability to land that position. So, of course, what happens is that the investigation comes back. It says we find that Newton was the first to developed the calculus is what they call it. For just a second, because I told you I would, let's talk about their particular notations. All right, Newton's notation. It's funny what Newton's notation looks like. In my mind, in this particular math history class, I find it very funny what Newton's notation looks like, because this is what it is. If you want to take a derivative of x, actually I think it's the derivative with respect to x, let's call it that, is the way he did it. His notation looks like this, x with a dot on top of it. Oh my goodness. That notation right there is distinctly in my mind Egyptian, right? And so, Newton, what are you thinking? This is bad notation for clear. We have issues. If I want to take the derivative with respect to x, I don't want to have to use that notation ever. So, of course, that doesn't work for us. Leibniz's notation, everybody probably knows it. If you've taken a calculus class, it is far superior, and it's the one that we use now. It's the dy dx, which we all know is the derivative of y with respect to x. And of course, this guy can be modified and changed. It can be a dt dx or a dx dy. It can be all kinds of stuff where, depending on what the formula or the function is and what variable I want to concern myself with, I can, of course, use that instead. So Leibniz is very good at using this as basically a slope or an average rate of change. And he's able to relate that back to algebra and the lowercase m, that kind of thing. He also comes up with stuff like the delta y, delta x. He's got that notation in there. He's got the limit. He's got infinity. He's got all kinds of notation that comes in. So limit as x goes to infinity. Let's talk about that one just a second. So we can totally see how Leibniz's notation and his understanding of all of the things that can be used here with the calculus and how it's applicable throughout life and in other areas comes into play, and you can see it a lot in his choice of notation, and of course that's the one that we have stuck with. So you should recognize a lot of that. The interesting things that come out of this particular controversy and what's considered to be the development of calculus is that we have a new mathematics that's developed, right? Think back. We've had a little bit of new mathematics with algebra being developed. Now we have a completely new mathematics with calculus being developed, that just takes us into all kinds of areas of analysis and different new mathematics that have been developed. We are basically just at the beginning of the 1700s now, right? So end of the 1600s, beginning of the 1700s, when we're going through this whole entire controversy. And again, let me go back. That's only 300-ish years ago, okay? And if you think about it, at the time of Newton and Leibniz, we're still traveling by horse. Still traveling by horse. Or cart with an oxen, that kind of thing, right? We're still in that kind of traveling mode. This is 1700. Just barely 300 years ago, right? Okay, really close to us. So think about it, all the extra mathematics that has developed since all of this, since the development of calculus. Think about how dynamic, how versatile things are now that we're very generalized with the algebra and with the calculus. Think about how just analysis in general has happened. And then let's think about some changes that have happened since all of this. So we're still traveling by horseback or by cart when calculus is developed. Since then, what have we had? We've had the industrial period, or some people might call it the industrial age. We've had the steam-powered period. We've had the internal combustion engine. We've had the electronics age. Just think about all of the inventions, just electronics alone. Okay, TVs and radios and computers and calculators and your cell phone and all kinds of things have been developed since in the last 300 years, basically, really recently. We've had the aviation age, learning how to fly. We've had the space race, just in the 1900s, right? So very recently, we've had the space race. We've had the computer age. I would argue there's probably a cell phone age or some kind of, I don't know, internet age or social media age, something like that we can throw in. Excuse me. So just all of these advances that have happened just in the last 300 to 350 years. Depending on how you want to count it, right? If you go back to 1666 and come up to our current years, the 2020s, then for sure we can count it like 350 years. Just in the last 350 years, so many changes, so many advances, and a lot of those changes can be tied back to the ideas that are developed in calculus in sequences and series. It's a big topic. In limits, derivatives, talking about integrals, talking about multiple variables. Oh my gosh, just thinking about the multiple variables studies. Oh, there's so much stuff in there. And then look at that and look at what's involved in computers today and how much of that can tie back into some topics that are basically calculus topics, right? Using tangents, there's just so much in there. So it really just puts a bit of a fine point on how much calculus has done for our modern age, and although we might be mad at Newton for hanging on to his knowledge for 20 years, at least he did finally publish it. He did finally get it out there. And thank goodness for Leibniz and his notation, because that is really amazing. And in my opinion, that really pushes the mathematics forward. So there is an entire PowerPoint on the notation of Leibniz for you guys to look at in your course. And that is the last of the big knowledge that we had to get through. And like I said at the beginning of this talk, I would like for you to also consider some other mathematicians. I might just put a list online for everybody to look at. More modern people starting in the 1700s-ish that we just don't have time to cover in our class. But the big one that you might see, say, on a final exam, again, I'll mention Gauss. So look at that, and thank you. I hope you've enjoyed hearing about the calculus controversy. Have a good day.